Hello and welcome to today's Containers 101 Tech Tuesday webinar brought to you by Insight Cloud and Data Center Transformation. I'm Amanda Sharp, Marketing Specialist at Insight, and will be your moderator today. Before we begin, I wanted to cover a few housekeeping items. This webcast is designed to be interactive between you and the presenters. The webcast console you are looking at can be completely customized. You can resize or move any of the windows that you have open. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. All questions from this webcast will be captured. If you are experiencing any technical difficulties, please visit the webcast help guide by clicking on the question mark icon below the presentation window. The help guide covers common technical issues. I would now like to turn our presentation over to our presenter, Chris Kapusta. Chris, the floor is yours.
Thanks, Amanda, and good afternoon, everyone. My name is Chris Kapusta. I'm a Principal Architect in Insight's Cloud and Data Center Transformation Group based out of Dallas, Texas. I appreciate everyone's time today to talk containers. So just a brief agenda that we're going to cover throughout the presentation today. Again, this is Containers 101, so if you've had some exposure to containers before, this is probably going to be a recap of what you already know. But there is a lot of buzz and even confusion in the marketplace, so we're taking this opportunity just to kind of walk through the basics. You know, why containers? How does it compare to things like VMware and other virtualization technologies? We'll go through some container basics, interacting with containers. What are the different properties we have to be aware of? Container runtimes versus container orchestration options that are out there, and then just a brief summary of the market. So what are some vendor container resource tools that are out there, and really how to help assess your options and make selections. If containers are even right for your environment, and then how do we go down that path in an intelligent manner. So we'll start off with kind of the why containers and how do they compare to virtual machines. And as we start here, we'll start with kind of why do virtual machines, why do technologies like VMware, Hyper-V, Acropolis, KVM, some of the others out in the marketplace, really why do they exist? And when we look at the history of computing, I'm sure as we all know, we started off kind of that centralized mainframe type computing. Open systems came about, and we distributed servers everywhere. So we took that mainframe kind of methodology and distributed across many servers. I'm sure we've all had server sprawl in our environments at one time or another. And what we found was we had those servers out there, but they really weren't consumed to their full potential. So we had a lot of money invested in them, and we were using maybe a fraction of a percent of what they could really handle from a capabilities perspective. So technologies like virtualization came around where we could take those resources, we could schedule them across many different workloads and virtual machines, and really help our CapEx spending. We're buying less servers because we're using what we have more efficiently, and we can also distribute that workload out there. Faster provisioning was added as kind of a benefit. What maybe was months or weeks of provisioning a server, deploying it, installing it, that cut down to days. And what you got was apps still get isolated at full access to the necessary libraries, services, host resource schedulers, and control of application resource consumption. And you got a lot of feature-rich management and operation tools to go along with that. And then the world changed a little bit. So in the 2010s, app consumption became more based on user demand. We found that monolithic apps can't scale or deliver features fast enough. If I've got to rev an entire application, put it through full regression testing and all of those functions to get it out in production, that adds a lot of time. And then the concept of cloud-native microservices came about, and DevOps, the idea of DevOps was born to meet those new demands. So that brought about the birth of microservices. Microservices versus micro apps are what you'll hear in the marketplace a lot, and really the difference between the two is just the size and scale. We adopted a single responsibility focus in our application development. So one service or one class or one library really should hyper-focus on one single functionality. we helped reduce dependencies, or we needed to reduce dependencies as we started to rev these applications faster. Scale out became very, very necessary to meet user demands. And we got the concept of cattles versus pets. So if you're not familiar with that, think of a traditional server environment. We treated our servers like pets. If one of them was sick, if one of them stopped working, we would troubleshoot it, we would care for it, we would patch it. With the cattle mentality and microservices, if something goes wrong, we destroy it and we build up a new one. So we really don't maintain them or care for them like we did a traditional server environment. And what the industry found was they needed a lightweight, ephemeral, and quick-to-deploy wrapper to contain all of this code and logic, and that's really where containers came from. So when you look at kind of the VMware versus containers comparison, VMware really is focused on that monolithic app. Now we can run containers inside of VMware. That's something a lot of organizations do today as they kind of go down that container path. But when you look at traditional virtualization, resource optimization, you get all of that with VMware. It must emulate the full virtual hardware, and it must account for all the underlying system requirements. You're still heavily reliant on an OS in a VM. There's built-in planning and management operations, and then there's true hardware-level isolation. So less chance for interference or exploitation from a VMware or virtualization point of view because you do have isolated access. Sorry, there's a little audio issue. Let me know if this is better. You do have isolated access to that hardware. So when we look at containers, they are more focused on microservices. Really, they're cloud native. They allow platform portability, so I can develop containers on-prem. I can move them into the public cloud. I can move them back, usually with little to no code change. They are ephemeral, so there's very few dependencies or state requirements, and they're usually very lightweight. So a container will only usually ship with just the code and libraries that it needs to perform that function, rather than think of a traditional virtual machine where I've got to have an entire underlying OS in that VM and all of the libraries and everything that comes along with that, maybe just to run a single application. None of that really applies in the container space. Now, I'm a visual person by nature, so maybe just a visual comparison of the two here. When we look on the left-hand side in purple, what a traditional VM deployment may look like. We have our virtual machine. They're all isolated. They all run their own guest OS. They all have their own binaries and libraries, and they all run one or more applications. There's a hypervisor and the underlying infrastructure below that. When we look at more of the container technology here, we can see we deploy the code we need for our app. We deploy any unique binaries or libraries that are not part of the container OS that it's running upon. Usually there's a container manager. One of the more popular ones out there is Docker. You'll hear that quite a bit. And then we have our host OS and infrastructure. So we have a little bit less abstraction between the underlying OS and the container itself versus a traditional virtualization model. And so to cut to the chase, to answer the question we started on here, containers are not the new VMware. They're actually very different technologies, and for all the right reasons, they should coexist inside of an environment. So if you hear messaging out there that containers are going to sweep the floor of virtual machines, we don't see it happening. Just the way that there's still a reliance on monolithic applications, they're not going away, and nor should they in a lot of reasons. But as applications spin up in more of a microservice architecture, it's a great use case for containers out there. And so these two should coexist inside of an environment, and for the foreseeable future, they probably will. So a little bit on the basics here. Again, Containers 101, so we're not going to necessarily go super deep in every topic here, but just wanted to start with a little bit of Linux versus Windows containers, excuse me. So really the container movement started in the Linux world. Today, Docker runs on any Linux system with kernel 3.10 or higher, and that kernel was actually distributed in 2011. Containers were actually a thing even before that kernel release, but Docker is really the one that kind of packaged it and made it a little bit more user-friendly to deploy at scale. Linux containers are usually small in size, as small as a few megabytes. Again, they're only distributing the binaries and libraries that application needs to run. Everything else it's going to share from the host OS itself. There's broad support for Linux containers across all public cloud providers, and there's really broad support from all the orchestration platforms out there. So a little bit later to the scene were Windows containers. And it's still somewhat in its infancy. It's getting more mature by the day. Both Docker and Microsoft are putting a lot of work into maturing that offering. Unlike the Linux side of the house that runs on pretty much anything since 2011, today Windows containers really only run on Windows 10 and Windows servers 2016 and 2019. For the most part, particularly in the Windows 10 space, Hyper-V is required for isolation and Linux container support. Windows 2016 actually does have native containers now without the Hyper-V requirement. Windows containers, pure Windows containers, are still relatively large in size. We don't get that small, fast startup that we get in the Linux world. So we're looking around 5 gigabytes per container today, just with all the dependencies that have to be put inside a pure Windows container. Now, you can run Linux containers on Windows, but one of the downsides currently is you can't run them side by side. You have to choose in Docker, do I want to run you have to choose in Docker, do I want to run Windows containers or Linux containers? You can switch between the two at any time, but you can't run them side by side just yet. And not all Docker operations are supported on Windows just yet either. Again, these are things we're working on as the offerings mature, but just be aware as you go down this path, Linux containers are much more mature than the Windows brethren, and probably will be for some time as development continues. So much like virtual machines, containers have their own networking setups as well. There's different ways and different use cases that we have for the different types of networks inside of the container space. The most popular is bridge networking, very similar to what you see in a lot of the virtualization offerings today. So it's the default internal network used for launching containers. The container traffic is isolated from host traffic. It's almost like a NAT operation there. I can open ports and pass through ports like a firewall type operation, but for the most part, my containers are isolated and can only talk on the ports that I pass through from a bridge networking perspective. The host networking, there's no isolation between the host network connectivity and the container network connectivity. So it'll use the same layer 2 and layer 3 IP of the host and communicate that way. There is an overlay network that's mainly used for multi-host environment. It allows back-end communication across hosts, but it's isolated to the container and Docker traffic there. And there's also a network called MAC VLAN, and this is probably more similar to what we'd see in a traditional ESXi or Hyper-V space out there. So this allows the container to be presented directly as a layer 2 device on the network. It gets its own MAC address, its own IP address, either DHCP or physically assigning a static IP. And this essentially bypasses all of Docker's networking kernel completely. It isolates it from the host, so it can't communicate with the host in this fashion, but it's also the easiest way to maybe take some legacy applications that we've containerized and need that kind of unrestricted flow on the network and allow it to function as a layer 2 device there. You can create your own networks within Docker, either using built-in Docker network drivers or third-party drivers. And to view the networks, if you're working on a system, there is that Docker network ls command. And we'll go through a few more commands throughout the presentation today. But just as you're looking to list the networks and understand what networks you have available to you, again, these are very Linux-like commands for those that have some familiarity with Linux out there. I can run that Docker network ls and get that information. So again, managing container networking, so just a few commands here. LS, as we talked about, list the networks available. If I need to remove a network, that's the RM command. If I need to inspect the network, again, this gives me some deep down details of each of the different network configurations. Or I can do a Docker network create and create my own network. So if you're familiar with Linux commands, for the most part, they're very similar, but all of the different elements of Docker kind of have the same command flow that we'll take a look at today. Container storage. So this is a big one to discuss because a lot of the messaging around containers is that they should be stateless and you should be able to stand them up and destroy them at any time and not have to worry about transferring state from one container to the other. And there is a lot of use cases where that's true. However, there is a use case where containers may need to share data either between each other or across states or between startup and shutdown, whatever that case may be. So Docker and most container engines allow a way to achieve persistence by exposing volumes or amounts from the host operating system, and this can be local storage inside of the container host itself, be it a Linux or Windows machine underneath that container engine, or this can be shared storage. As we take a look at later in this presentation, a lot of the more popular storage vendors out there offer container plugins and orchestration even to present persistent storage to these containers to help preserve data in between instantiations. And again, this is important because there may be data generated by these containers that we need to protect, we need to secure, we need to have available for other functions within the business. So it's important to understand that we can do that with containers, either by mounting volumes, and again, this can be local to the container OS or a shared storage device. We can also do bindings as well, and this will basically mount a file system or directory right off the container host into that container. So just a couple different options that you have available to you should you need to persist storage between container instantiation. We also have the ability to control resources. So inside of VMware, inside of Hyper-V, I have the ability to set shares and control how much a VM can consume of CPU, of memory, of disk. I do have those somewhat basic functionalities inside of containers as well. Again, nowhere near as robust as what you can do in say the virtualization technologies today. But I can control things like memory allocation, memory swap, kernel memory access. For CPUs, I can set number of CPUs that container can consume. I can also set shares, which you can see is equivalent to the kind of process priority that you'll see in other virtualization technologies. I can set security, computation profiles, and even AppArmor profiles. So for those familiar with SC Linux, Secure Enterprise Linux, it's really kind of bringing those methodologies into the container space as well. And then just kind of taking some of these concepts and really just running your first container. So if you want to go through this after the presentation or even as while we go through it today, but I just wanted to go through a few of the concepts of how do we pull a container image down, how do we run a container, how do we interact and destroy and manipulate a container. So you can see the first command here. We're going to use the hello world container. If you've ever taken a programming class or anything like that, usually the first thing they have you do is write a program that just says hello world. So there's a container out there that does the same thing. And so the first command we run here is that docker pull hello-world. And so what that's telling the container engine to do is to go out to the public repository, find the container called hello world, and pull that code down to your system to get it ready to run. So Docker and a few others maintain public registries for containers. Your organization can spin up its own registry, and you can have your containers internal. So just very similar to, say, the VM marketplace versus building your own templates and VMs. Very similar concepts there. So once we have that code pulled down, we actually need to create the container. Very simple, Docker create. You can give it a friendly name. I just called it Hello World here just to keep with that naming methodology. So what we have now is we have a container that's kind of in an off state. It's been instantiated. It's got a unique ID that it's going to run under, but it hasn't really done anything yet. And so that Docker run command is going to actually run the code inside of that container. And again, these are very quick to boot up. If you run through this exercise on your own, you'll see how quickly it runs here. Just keep in mind we're not booting an entire OS again like we are in that traditional VM sense. We're only executing the code that's contained inside of that container. It may have some unique libraries that it loads, but for the most part, it's going to share as much as it can from that underlying host OS. And then once our container runs, if we need to delete it, this one just happens to run and exit. There is a stop command as well if you're running one that doesn't run and exit immediately. But once we need to delete it, just that Docker RM command, and that will delete the instance of the container, but it'll still leave all that underlying code that you pulled from the registry on your system. So just keep in mind if I need to spin that up again, or I need to update that code, it's still living there, and it's just going to layer any changes on top of that, or just reinstantiate that container. And so we kind of did the step-by-step there to kind of show the different traditional steps that you go through when pulling and running containers. Just know that container engines like Docker are smart enough to kind of combine all of those steps at once. So let's say I didn't have this code at all. I just sit down at my console and I run a Docker run hello world. It's smart enough to say, hey, you don't have that code available to you. I'm going to go pull the latest from the registry. I'm going to bring it down. I'm going to instantiate it, and I'm going to actually run it. So we can combine those commands to make it a little bit easier to use, but just know if I don't feel like doing step-by-steps here, there is a lot of intelligence built around that as well. And then just some other useful commands. So Docker PS will show you running containers. Again, if you've used a Linux system before, PS generally shows you your running processes. So a lot of these are very similar. Docker image ls will show you what downloaded images you have to your system, as well as what versions. A lot of developers will tag their containers with different versions, either latest or 1.0, 2.0, etc. So you can do kind of version control and versioning of the container images. So if we have an upgrade that goes wrong and we need to roll back to a previous version, we can maintain them that way. And then Docker stop, we didn't run this before just because the container we ran kind of exited after it executed its hello world. If you have a running container you need to stop, it's just a simple Docker stop command. So that's all nice and good for containers that exist out there, but how do I actually build my own? Or how do I define my own even from existing containers that are out there? And that's where the Dockerfile comes into play. So the Dockerfile is really your source code for your container, used alongside the Docker build command. This will basically describe what your container should look like, what libraries and code it should contain, how it should execute, what network ports it needs to function, all of the very similar in concept, let's say, to a VMX file that describes the configuration of a virtual machine. These are generally stored in source control, so if I need to do source control around them, GitHub, some of the other ones out there, you can store those there. Docker uses layering to reduce overall disk space, so we'll take a look at what that entails here as we have an example Dockerfile, but we kind of layer the different components that it needs. So any binaries or libraries it needs, any specialized code, anything it's got to pull down from a repository or a source control, all of those different are what's called layers inside of a Dockerfile. And there's two major best practices around these. High change commands should go as low as possible in a Dockerfile, and you should try and chain as many steps into a single line as possible. So again, helping cut down on execution time, helping cut down on if there's static stuff that doesn't change a lot, we want to define that first. So when we do get to the high change areas, it's not waiting to run that there. So just some commands you'll see inside of the Dockerfile, add and copy. These both kind of function the same way, where they move data from a build machine into a Docker container. Really the major difference between the two is add can pull from URLs as well. And then environment, ENV, exposes environment variables to the container. ARG is used the same as ENV, but really only during the build phase. And the run command is any command that that container will actually run internally. So you can just see some of the examples there. Volume, again, forces a volume to be created for persistent data. Our working directory, expose, will tell us what ports we need to expose when this container is run. And then starting the container process. So CMD sets the default command. Entry point configures a container that will run as an executable. So what I've done here is just kind of put together an example Dockerfile. You can see we're from here is we're using CentOS 7 as kind of our base environment. We're setting some environment variables. We're running some yum commands to install HTTPD, which is a web server. We're echoing a variable here. We're setting our working directory. We're copying a file from our build machine into var www HTML. We're telling it that it has to expose port 80, and we're setting our entry point, which is really the executable directory for the web server there. So obviously a very simplistic Dockerfile there, but as we look at it, you know, what would we do to make this live? Let's assume I name that Dockerfile Chris Demo. These are just the commands I would run to rather than pulling the container down, just building it from scratch and actually instantiating a custom build container. So I do that Docker build command. I pass it my Dockerfile. I run I run that container now that I've built off of my Dockerfile, so I can see the name I gave it was Chris Demo. I passed in an environment variable for that foo that we set inside of the Dockerfile. Again, I've mapped port 80 to port 80, and I've given it, I've told it what to run off of here. And I can see if I need to debug that. So again, these containers, there's no GUI for the most part. If I need to interact or troubleshoot logs or anything from a container perspective and I need to get inside of that container, I can do a Docker exec, log in as root here, and get access to the bash shell inside of that container. And then Docker kill will stop and kill it, and I can remove image once I'm done here and clean up the image that I've downloaded and built off that Dockerfile. So very simplistic build process here. Again, it's Containers 101, just to kind of show what that looks like of building my own versus using something already available in a registry. So we've focused heavily on the runtime, in particular Docker, as it's one of the more popular runtimes out there, but there's also a lot of orchestration built around containers as well. And so, Docker runtime is the underlying library that allows containers to run. But if you look at running these at scale and running these in an enterprise, you're probably not going to go run these Docker commands every single time you need to start up, pull down, or destroy a container. You want some orchestration around that, and you want high availability, and you want multi-host scheduling. So you can see some of the things here that orchestration adds on top of just basic container maintenance. So multi-host scheduling, service meshes, which is load balancing, routing, things like that. Container repositories, some advanced scheduling of containers, CI/CD pipeline control, failover capabilities, everything you'd expect in a more enterprise-ready solution than a one-off Docker server. So there's a lot of orchestration out there. You can see some of the examples here. Obviously, Kubernetes, for the most part, industry-wide, seems to kind of be winning that orchestration space, but it's definitely not the only one available. all the public clouds, Azure, AWS, GCP, some of the big ones out there, obviously focus a lot on Kubernetes and offer Kubernetes services. But if you're looking to run containers on-prem, there is a lot of orchestration around that as well, either built around Kubernetes or even a replacement too. So just be aware that there is a lot of orchestration around the containers, and really it's evaluating those different ones to understand which makes the most sense in our container strategy. So we wanted to kind of talk about the market. A lot of vendors that some of the more popular vendors on the market have a lot of plugins and orchestration around containers. So what I wanted to do is just take a couple minutes here and walk through some of them. Again, this list is in no way exhaustive, so don't think these are the only options out there. But we did want to cover some of the options from some of our different partners out there. So NetApp, they have what they call their NetApp's Kubernetes service, and this is actually a SaaS offering that you can just consume through cloud.netapp.com. If you visit that website, you can kind of see a consolidation of all of their cloud offerings, but the NetApp Kubernetes service really it sets out to integrate NetApp storage with your Kubernetes and container infrastructure. So again, we talked about the importance of that persistent storage and being able to share it and protect it and secure it and everything else we do with our normal data there. They're looking to really make that process easier. They support the big three from a public cloud provider, AWS, Azure, GCP. It also is available on-prem on the NetApp HCI platform, but has not fully rolled out beyond that just yet. So Pure Storage, the Pure Service Orchestrator, really what that does is it federates your different Pure arrays together, wraps a single API around it, really storage as a service type of offering, and that integrates with Kubernetes and Docker. So if you need, again, really focusing on that persistent storage and managing that storage that these containers need to run and share data. They do have different drivers specifically for Kubernetes as well as Docker. So if you just need a storage plugin driver and you have a Pure array, those are the options available to you today from Pure. Cisco, the Cisco container platform, that's actually an on-prem and cloud solution. Basically GUI-based cluster deployment. So a lot of the tools around containers and orchestration today are not GUI-based. We see a lot of vendors in the marketplace today kind of wrapping a GUI around that to make management a little easier. Obviously, Cisco being a networking shop, first and foremost, they have a lot of plugins around container networking. And even bringing ACI into that space, they offer a lot of monitoring as well as storage configuration. Nutanix, so Nutanix Carbon is their offering around Kubernetes clusters, again with storage integration, heavy focus on-prem today. They do offer a persistent storage plugin for Docker as well as the Kubernetes volume plugin. So persistent storage for Kubernetes clusters. So again, you'll see a lot of the theme as we go through this here is from their traditional storage partners providing that plugin to make integrating storage into your orchestration and container strategy very easy. HPE has the Nimble Storage Docker Volume plugin, 3-PAR Volume Docker plugin. There is also the HPE Container Platform. They've kind of combined a few different technologies that you can see there, again, to wrap some GUI and container orchestration around container management. And then Dell Technologies with their Pivotal Container Service, as well as what they call RexRay. So again, looking at ways to integrate that storage management into the container orchestration, something that native container management and orchestration really doesn't tackle that well today on its own. Again, this list is nowhere near exhaustive. There's a lot of technologies out there like Diamante that are providing really a whole stack around containers and Kubernetes management and helping with that ease of deployment, almost what we're used to from some of the non-container technologies today. So this market's ever changing. There's a lot of interesting players joining the race alongside some of the ones that have been here for a while. So again, if you need help navigating those waters, That's what we're here for. And then the path to containers. So just kind of finishing up here with, are containers right for our organization? How do we know if we should even go down this path? You'll hear a lot of magazines and market speech say, what's your container strategy? And so it's not an all or nothing is the first thing to remember. Virtual machines are not going away. Monolithic applications are not going away for the foreseeable future. And in a lot of cases, they shouldn't. They're not inherently bad. They can coexist and they should coexist. In fact, a lot of our customers who are first dipping their toes into containers do it on VMware. I put a Linux VM on VMware. I start deploying containers on it, and that's a great way to kind of dip your toe in the water and kind of become more familiar and mature with containers, and then move on to some of these more specialized solutions. Applications need to be rewritten for the most part to take advantage of microservices, and you have to ask, your organization has to ask yourself, is it worth the time and the money? What are we going to get out of this by turning an application into a microservice application that we're not getting today? If I have a customer that went down this path with their mobile application, so they needed something that mobile apps are they're very unpredictable from user engagement. Some days you may have 1,000 users on their iPhones or Android phones. Some days you may have 10 or 100,000. How do you build out an infrastructure for that? So their solution was to look at a microservice strategy around that application and be able to spin up and spin down containers as demand required, as scale required. And that's not something we can traditionally do easily with monolithic applications. So for the most part, they need to be rewritten. And again, they're not inherently bad. It's okay if they stick around and consume VMs or physical servers or whatever it is. That's not necessarily a bad thing as long as it makes sense to the organization. And then it's got to align with your cloud strategy. Again, one of the key functions and benefits of containers is it does allow portability, somewhat easy portability between on-prem and cloud workloads. The container I write on-prem and run on-prem today can probably be deployed with little to no changes into a cloud provider tomorrow. And I know we can kind of do the same thing in the virtual space. If I run ESX in Azure or AWS, I can migrate VMs back and forth, but there's overhead in there that the container space just doesn't see today. And it's weighing your options between traditional IaaS in the cloud, PaaS in the cloud, containers in the cloud, or a combination of all of them. So these are all just things we need to be aware of as we assess our container strategy and move in that direction. And then, is my environment ready to consume containers? It's easy to say I can just spin up a Linux system and deploy containers, or even a Windows system and deploy containers. But again, how do I share data? How do I secure them? What are my networking requirements, and do they meet the needs and demands of what containers are going to bring to that environment? How do I secure the data? How do I back up the data? Data protection in the container space, for the most part, still in its infancy, and there's different ways vendors tackle it today by side loading other containers to access the data, but it's definitely not at its maturity yet. That's for sure. And then, last year, what's my environment's or what's my organization's Linux knowledge? There are a lot of 100% Windows shops out there, and there's nothing wrong with that. But again, Windows containers are nowhere near mature or as flexible or as even small as Linux containers today. So if an organization is moving down that path, and I want that cloud portability, Linux is probably the way to go. And are we familiar enough with that technology to support it? So these are just some questions that we're helping us answer. Customers are asking. Again, if we can help with any of that knowledge or insight, no pun intended, we're here to do that. So that's what I had today from kind of Containers 101 perspective. I haven't seen any questions come in yet, but I'll leave a couple minutes here for questions and anything else I can answer. I'm going to do a last call here. And yeah, I was going to say I'll do a last call and then turn it back over to you, Amanda.
All right.
All right, I'll say go ahead, Amanda, back over to you.
All right. Thanks, Chris. Thank you for attending today's webcast. An on-demand version of this webcast will be available within 2 to 3 days. You will receive an email notification once the recording is available. Thank you again for participating in our webinar, and have a great day.